Good afternoon, I am Mr. Ish. Thank you for joining me. In this video, we are looking here at the concept of molality, and we are looking at freezing point depression and boiling point elevation by means of this comprehensive question. We are starting out here with 250 milliliters of 5 molar glucose solution, which is diluted to 1.5 liters of solution. We have to find the freezing point and the boiling point of the resulting solution. Assume the universal solvent here is water, and assume the density is 1.06 grams per ml. Given you're starting here with something with molarity and a volume, we have a resulting volume and we have to find everything else. You know, molality is symbolized with a lowercase m is always equal to moles of your solute, which you know here is glucose, and divided by the kilograms of solvent, which you know here will be water because that's our universal solvent. We also know molarity, capital M, is equal to moles divided by liters of solution. We have all of this. What you can do here to start out this question is determine the moles. We have 250 ml of 5 molar glucose. We know molarity is equal to moles over liter, so therefore molarity times your liters will give you your moles of glucose, and that's exactly what we need to do. We have 5 and 250 ml, but everything here should be in liters. We'll do 0.25 liters times 5, and that'll give me 1.25 moles of glucose. 1.25 moles glucose. It's also not a bad idea to multiply this by the molecular weight of glucose because it will help us determine the mass. Why do we need to know that? Because it will come into the play when we're talking about the kilograms of solution, from which we have to then determine the kilograms of solvent by minusing the kilograms of solute. And how can you determine the grams of glucose? Well, you know you have moles times molecular weight is equal to mass. And what's glucose? C6H12O6. You know you can run that through the periodic table. You'll have 6 times 12 plus 12 plus 6 times 16, 180 grams per mole. So 180 times 1.25, I get here 225 grams of glucose is what I have. Let's determine the molality. The molality is equal to moles, which we have right here, 1.25 divided by kilograms of solvent. The kilograms of solvent is equal to what? Kilograms of solution minus kilograms of solute will give me kilograms of solvent. Why is this the equation? Because your grams or kilograms of solute plus grams or kilograms of solvent gives you the mass of the solution. So that's exactly what we have to do. And how can we determine what the kilograms of solution is? From right here. The resulting solution is 1.5. You do 1.5 liters times 1000 ml per 1 liter. Why am I converting to milliliters? Because the density here has a factor in terms of milliliters times the density factor to convert the volume into mass, grams per ml. You have to multiply and you'll see the liters cancel out, the milliliters cancel out. The only thing which will remain here will be your grams. You'll have 1.5 times 1000 times 1.06. You'll have 1590. 1590 grams, which is 1.59 kilograms. Let's keep everything here in grams for right now. I already know my grams of solution. I know my grams of the solute, and I can determine the grams of solvent. I'll do 1590 grams minus 225 grams, which is the grams coming from the moles of glucose. I have 1365 grams of solvent, which is 1.365 kilograms. 1365 grams of solvent is 1.365 kilograms of solvent. You have everything now coming into play for this molality determination, and that's what we need to do. You'll do 1.25 divided by 1.365. You'll get 0.91575, a value I will save in my memory of the calculator. It's 0.91575 molality. Now let's determine the freezing point. The change in the freezing point is always equal to, with regards to your reference for your freezing point for water, is 0 degrees. Anyhow, the formula is Kf times molality. I know for water is 1.86. Forget about the units, and the molality is 0.91575. We'll multiply that by 1.86. I have saved the value here. I'll multiply by 1.86. I get a value 1.7. What does this 1.7 mean? Well, it's a change in the freezing point. Our freezing point will be equal to 0 minus 1.7 degrees Celsius, which is minus 1.7 degrees Celsius. And that's my one answer right here. Minus 1.7 degrees Celsius is my new freezing point of this water solution in which you have a certain amount of glucose. That glucose has effectively depressed the freezing point, and the calculation is right here. Now what we have to do is determine the boiling point elevation, because the glucose in that water in terms of solute particles will elevate the boiling point of normal water to something higher. And what will that be? Your boiling point elevation is going to be the boiling point constant for water times your molality, which here is 0.512 times 0.91575, and we'll see what this value is. Everything with regards to 100 degrees as a reference for the boiling point of water. So we have 0.512 times that saved value. I get 0.4688, which I'll round to 0.47 degrees Celsius. But this is with regards to 100. So I'll have 100.47, and that'll be my new boiling temperature. Instead of water boiling at 100 degrees, it'll be 0.47 degrees higher. It'll boil at 100.47 degrees Celsius due to the presence of this glucose solute in the water. So what have we seen so far? We had something here starting with molarity, which we converted into molality by means of the gram calculations that you saw, everything with regards to mass. We converted the moles to grams. We determined the kilograms of solvent by doing kilograms of solution, or grams of solution minus grams of solute, which gives us this. The molality is equal to moles of solute divided by kilogram of solvent. The molality factor is necessary for determination of freezing point and boiling point changes, and you see that there's a specific constant here for boiling point change, and there's a specific constant for the freezing point depression, and all of that has been laid out for you. The answer to the two parts of this question are right over here, and everything should be right. Thank you for joining me. Have a good day.